In this video, I'm going to explain the relationship between force and the distance. The work done can be represented graphically by using a force distance graph. This graph, we use two positive axes. On the vertical line, we plot the force and always provide the SI unit in newtons. On the horizontal, we plot the distance in meters with SI unit. Now, the area underneath the graph represents the work done. Work done is a force times distance. So if you have this area, you multiply this side and this side, you get the work done. Now, it depends on the shape that is underneath the graph. If a shape is a rectangle, a formula, an area to calculate an area of a rectangle is length times breadth. And in place of area, since it represents a work done, it will be W equal to L times B. On the L, you have force. On the other side, you have distance, which is work done. But if a shape is a triangle, the formula will be half times base times height. And where there is area is W for work done. And we can calculate it by saying half times base times height, because a triangle is half of the rectangle. So you get that area that is under the graph. Now, if the mass of the object is given in kilograms, it has to be converted to newtons because the name of a graph is force distance. When changing from kilograms to newtons, you multiply by 9,8. Change a weight or the mass to newton. It can also be given in tons. The relationship between a ton and a kilogram is that a single ton is equivalent to 1,000 kilograms. So you multiply by 1,000 to take it from tons to kilograms. Then you multiply by 1,000 to take it from kilograms, you multiply by 9,8 to take it to newtons. The weight of the object can be given in megagrams, grams, but always take it to newtons. Let's look at the next slide. Two types of graphs. Now we can have a graph with a constant mass or a constant weight or a constant force when the force of the object is not changing. So it will be represented by a straight line. If something is constant, it will be this line, its weight is not changing. Whether it's moving for 50 meters, for as long its weight is not changing, it will be represented by a straight line, but the distance is increasing. Now the formula, since this is a rectangle, to calculate a work done, it will be length times breadth. It will be this side and this side to get your work done. Another shape that you can have is between an object with a length. We can have a chain, a rope, a spring, or a cable. The shape would be a sloping line because if you are pulling a rope, you're winding it up, a rope will get shorter and wind up. But if you are lowering a cable, it will get longer as you lower it. So let's say you are lowering it from 0 as it is reaching its destination down, the length is getting longer, it's increasing. But if you are winding it up, it will start from a bigger length, just like this graph, and get shorter as it is reaching its destination. Now let's look at the next slide. The next slide will be the combination of the two. We can have a graph that combines a cable and a weight or the object that is not changing its weight, or an object with constant weight. So if it's being hoisted up, the object is there represented by horizontal graph, but the cable or a chain, it will get shorter as you hoist it up. Number 2, graph number 2, this one is lowered down. Even if you are lowering an object down, at any position, its weight will stay the same. But as you lower it down, the rope will be getting longer. So the graph will be like this. Let's have a look at this. The first diagram there, we have a drum there. Let's say this drum is resting on a platform. And there is a motor that is operating or driving the drum. Now let's assume that it's rotating this direction. So if it's rotating this direction, as it is rotating, and let's say initially this length is 50 meters. So when we represent it graphically, this is the graph, and 0, 10, 20, we can put 10, 20, 30, 40, up to 50. So it's gonna start at 50 because we want to hoist it from this point. This is the starting point. Even the load will be there. So this is the load, which is this load. At 50 meters, there is a load. But attached to this load, there is this rope. So there will be a rope will be attached there. Now, if this drum is rotating in this direction, it means it will be winding up this rope. So let's say if it's winding up it up to this point, when W is at this point, this rope is no longer 50, it's getting shorter. So the rope, as the load is moving up, is getting shorter. At this point, it will even get shorter than it was at this point. So it will get shorter until the total weight and the rope are both on top of the column. So it will wind up until you have something like this. Both the weight and the load are on top of the column. So if both the load and the cable are on top of the column, it means what you have here will be the weight plus the cable or plus the rope. So the weight is the load until both are on top. But what you have here is the weight alone and the cable that is getting shorter. So if the distance is 30, is shorter. At 20, shorter until the total length is winded up and the load is on top, is hoisted. Now let's look at the second graph. Now this one is on top, both the weight and the load are, and the cable are on top. So what we have there is the combination of the two. But the weight is not changing, so this is W there. What happens to the rope? What happens to the rope? As you lower it down, it's starting from 0, it's attached to the load. So it's starting from 0. As you lower it down from stage 1, it's getting longer. This one is 100, 100 down. As you lower it at 1, it's getting longer. At 2, longer than it was at 1. At 3, until it reaches 100 meters. So the rope will get longer. This is how the length is increasing in that direction for the rope. So in this graph, you can be calculating the weight of the chain. You can be calculating the work done. The work done is the area under the graph. Total work done, area under the graph. So when you're calculating the work done for both graphs, if it's for the total work done, W will be equal to A1 plus A2 because there are two areas. And the shape is the half times base times height plus L times B. Unless the question says calculate for the cable alone or calculate for the load alone, you're only going to focus on the area under the cable alone. Number 2, we can calculate the average force or the average tension. So the F average will be equal to we have this force here, the first force, which is W. And the second force that we have is between these two forces. The second force that we have there is that of the load plus the chain. So we can call this one is the weight, not the work done, it's the weight. Plus, this one will be the weight plus cable. So it will be W for weight plus the cable. Then since we are looking for the average, we divide this by 2. It will give us average. Now to calculate a work done, you have 2 options. Since you do have the average force, a work done can be given by F average multiplied by distance, or work done can be given by the area underneath the graph. So there are 2 formulas to calculate work done. Is the force average multiplied by the distance, or is the area method. Now, the average force, a question can say it is the tension, a force is a tension. Is a tension or is the average tension? It's the average tension, F average for force average. We can also calculate the power, just like you calculate it on a horizontal and on a vertical plane. So power will be equal to work done over time. But if you do not want to use work done over time, you want to use the force average. The power will be equal to force average. Since we have 2 forces, it will be multiplied by distance over time. Also, since we have distance or displacement over time, this power can be given by force average multiplied by velocity, because S over T is V equal to S over T. Now let's look at the example. Example 1. In figure 2 below, the force distance graph of a lift of 2,500 being lowered. This one is lowered over a distance of 5 meters is shown. So you are given the weight of the lift. So a lift won't change its weight at any position. So there is the graph for the lift, 250. Is being lowered over a distance of 5. So this is the distance of 5. Since it is lowered, the cable is starting from 0 and the cable is getting longer. Now, first question says, use the graph to determine the following. The weight of the cable in Newton meters. So what we have there, the solution. The solution to this graph. I'm going to display it this side so that you can see how to sketch this graph of a force distance. Now, first thing we are looking for the weight of the cable in Newton meter, and the distance is 5. Let's have a look at it. Distance is 5 here. This is 0. Remember on top or there at that point, this is the combination of a weight plus a cable. This total is for both. So if we have that total for both, it means a cable will be equal to, because we do have weight here, this one is for the weight of the lift alone. So it will be 2,800 minus 2,500. And the answer for the cable here will be 300 newtons. So once you get once you get the difference between the newtons will also be equal to a newton. Difference between a newton and a newton will be a newton. Now, we need to get this one. We got the weight of the cable per meter. This plus this is equal to that total. So the lift plus cable is equal to this. Lift plus a cable is equal to this. So when you make a cable the subject, it will be this bigger minus the smaller and get the cable. But this one is in Newton. The question says get it per meter. So when we want the cable per meter, we're going to divide by the total length of a cable so that we get it on a single meter. So it will be equal to 300 divided by 5, which is the total length. And 300 divided by 5 will be 60 Newton per meter. So this is the length of the cable. Now let's look at the second question. The second question is looking for the total work done while lowering the lift and the cable. Total work done. So it will be the total area under the graph. Now let's look at the solution of the total work done. The solution of the total work done under the graph. Total work done, WT for total will be equal to, we can call this A1, this one A2, it doesn't matter. It will be A1 plus A2. And the dimensions of A1, this is a rectangle, so it's L times B. But A2 is the half times base times height. So this one is 2,500 by 5 plus half times base of this triangle is 5. But the height of the triangle is from this point to this point. That is the height of the triangle. So from here to here is 2,800. But from here to here is 2,500. So this distance here is 2,800 minus 2,500. So you're gonna see the height will be the length of the, will be the weight of the chain. When you minus 2,800, 2,500 from 2,800, you get what? 3,000. So the height there is 300, get 300. Now 2,000, use a calculator to get your answer. 2,500 times 5. The answer for this side is 12500 plus a half, 0.5 for half, multiply by 5, multiply by 300. And the answer for this side is 750. So you add the 2 plus 12500, and it is 13250 joules. That is the work done. Work done is measured in joules. Alternatively, when you calculate work done, you can use the average force or the average tension. So this is the or let me do it this side, or F average will be equal to weight, which is 2,500, plus is the first force plus the second force. The second one is 2,800. So to get average between the two forces or two velocities, you divide by 2. And the answer here of average force will be 2,500 plus 2,800. Then we divide this by 2. The answer is 2650. 2650. So this is the average force. Now using the average force to calculate work done, it will be W equal to F average multiplied by a distance. It said the total. So it will be the total distance. So the average will be 2650 multiplied by 5. And the answer here, when you multiply 2650 by 5, The answer is the same. It is 13250. 13250 joules. Now let's look at the third question. The third question says, calculate the power required if the time taken to lower the lift is 30 seconds. So in this question, you are looking for P and T is given as 30 seconds. Let's look at the solution. So T is given as 30 seconds. The formulas for power is that power can be work done over time, or power can be F average multiplied by distance, or power distance over time, right? Or power can be equal to F multiplied by V, since this is velocity. So I'm going to choose the one that uses work done, and they prove it using the one that uses average force. So if we're using the work done, power will be equal to, work done is 13250 divided by, time must always be in seconds when you calculate power, so that you get a joule per second, which is equivalent to a watt. Joule per second is equivalent to a watt. So power must be in those units. So time is 30. 13250 divided by 30, the answer will be 441,667. 441,667 watts. That is the power. So if we use a formula, or P equal to F average multiplied by distance over time. This is velocity, so you can calculate velocity aside. Remember, in some question you'll be given velocity, which is, you just go straight to this formula of FE. Or get work done first and use velocity to get time. Now the F average, this was the average force, 2650 multiplied by, it says total. So it will be multiplied by 5 divided by, the time remains 30. 2650 times 5 is going to give us this answer. And we divide it by 30, still we're going to get the same answer of 441,667 watts. This is how you do it. Both formulas are correct, but you need to remember, if you are using the forces or the tensions, you must find the average first, because it's two forces. So find average between the two and divide by 2 to get the average. Thank you.